Couple of years back, I had conducted one talk in front of some architects and youngsters. I asked them one simple question. How many of you like your grandparents' house in your villages? And as expected, almost all of them raised their hands and said that we really loved the place. Now, then I asked that were these houses designed as per architectural principles of aesthetics and harmony, rhythm, and whatnot? And most of them told me that no, they were all very simple houses, and we have a lot of lovely memories there, which was expected. Then I asked that what is it about these houses which made them so endearing? So out came various explanations. My relatives were there, my grandparents, and all those memories and conversations and laughter and all that. What is interesting is that as life happens, architecture stands around those happenings as a silent servant, supporting that particular activity. Good architecture, that is. And then I started thinking, suppose if we wanted to kind of achieve the same kind of endearing architecture, or at least make architecture that supportive servant for such endearing experiences, how do we go about doing that? Because there seems to be a spectrum of complexity from very simple to pretty complex in anything which we do, which should include architecture also. But then, how do we zero in into that level of simplicity or complexity, whatever the case may be, that we want to achieve? And how do you go about doing this? Now, one of the things which I've been advocating is a concept known as abductive reasoning in our designing. Now, some of the architects, when I mention this, they kind of get a little uh, offended, or maybe they think it is just too technical and impractical and whatnot. But look at it very neutrally. A lot of our designing, if we go about doing it with a kind of a one direction, just move in one direction, take a concept and then go ahead with that. What is it that assures us that that is going to lead to that destination that we want? So, for very unemotional reasons, we should really first consider a multiple set of alternatives and then choose the one which fits the right objectives and the right criteria that we are searching for. I don't see any other way by which we can really do this. So, but then many people don't end up doing abductive reasoning is because taking out one design itself and fleshing it out is such a difficult task, which is where actually technology helps, but that I'll talk about later. Today, we can do that, and that's why all these videos that I'm making. But let me get back to this topic about complexity scaling. How do you establish that? Suppose we have to compare between various alternatives that we have worked out for a design, and we have a kind of an idea that it should be quite a simple design or quite a complex design, whatever the case may be. How do we zero in and pinpoint that we have definitely reached that? Maybe not pinpoint, that's the wrong word, but broadly, like that we have reached that particular point where among say 10 alternatives, we find that this particular alternative fits that complexity scale the way we want it. So here are some tentative hypotheses once again, because to really exercise this, there's a lot of work which needs to be done cooperatively amongst a lot of architects. Only then we can then start using this data. So let me kind of introduce this topic of complexity in architecture and how do we start measuring that. To get a clue, there are some interesting lessons from uh, fields like linguistics and music and other such subject, information theory. So let me borrow some very useful concepts from there, uh, and then we can come back into architecture and then explore this how it can be used in architecture. So let me start with a very interesting song from the Beatles, composed by John Lennon, an extremely unusual song and quite an offbeat song. Frankly, I don't like that particular song because I don't consider it particularly musical, but it is probably a philosophical statement. And that's a very good starting point to understand this complexity scale. So, this song that I'm referring to is called Revolution Number Nine. If you hear that song, you'll find that it is so strange. It just has got two words which gets repeated again and again all the time. That's number nine, number nine. It just John Lennon just keeps going on with that. Number nine, number nine, number nine. And in the backdrop of uttering those words, I won't call it singing. There is this whole cacophony of noises and people yelling in the backdrop and all kinds of weird sounds are going on, and there is no real pattern to it at all. But the only pattern which you can recognize is this number nine, number nine, number nine. It just goes on in various parts of the song. So I think John Lennon was trying to make a point about revolution, which is a kind of a contrast between something very, very simple, which is the uttering of these words, number nine, number nine, number nine, the whole time, and a backdrop of extreme chaotic noises and sounds and everything, which kind of reflects that possibly that what you thought was simple is actually trying to camouflage what is very, very chaotic and complex, something along those lines. Well, this talk is not really about the philosophical meaning of that song, but using that as a starting point to explain complexity. Now, in information theory, there is Claude Shannon who came up with how to measure complexity using a concept called entropy, uh, which is quite interesting and you should look it up. But I'm not going to go into in that direction. Instead, I am going to talk about a Russian mathematician's work. In fact, this particular point was discovered by three different mathematicians, but it is mainly attributed to that Russian mathematician Kolmogorov. So it's called Kolmogorov complexity. Since it's hard to pronounce and I may mispronounce it, so I'll call it K complexity. Now, this K complexity is a real thing which can really measure, uh, can be used as a method of measuring complexity. And that, to understand how that happens, it's not very difficult. So, let me give you an example. Suppose let me take that song itself, number nine, number nine, number nine, right? That's all what is going on in that song as far as decipherable words are concerned. So instead of writing each word separately, you can mathematically describe it as okay, 50 number nines. Okay, so with three words, 50 number nines, I've explained the whole song. So what this means is that if you were to compress that set of words, it'll compress it very, very to a very small amount. What does that mean? What does compression mean? Now, Kolmogorov complexity has got a particular definition. You can look it up. It's all about what is the minimum size of a computer program which can be equivalent to a particular set of words or whatever symbols which you're trying to describe. But I'm simplifying it by looking at it as a compression. So we have all used compression. We have all created zip files. And if you must have zipped up, say, a text file, you'll find that the zip file becomes very small. Why so? Because there are a fair amount of patterns usually in that text file. For example, the word the or the letter e, they are quite repeated in many places. So you can kind of make out patterns. So internally, the zipping algorithm would try to squeeze all of them together and put a number next to it. Say, okay, there are so many e or so many the. I'm very, very crudely explaining the zipping algorithm. It is not as simple as this, but it is somewhat in that direction. Conceptually, it is like that. Whereas if you were to zip up an image or a video file, you find that it doesn't zip up, it doesn't compress too much. The reason is that there are no very easily detectable patterns. So you can't just, how much ever you squeeze it, there's nothing much which can be squeezed over there. So the ratio of the original string, it's called in programming, or the original sentence, uh, vis-a-vis the compression of that sentence, that ratio, if the compression is very high, then you'll say that the complexity, the K complexity is quite low. If it doesn't compress so much, then the K complexity is quite high. So you have in information theory a method, a way to sit down and work out between various different types of complexities and different levels of complexities. So to go back to the Beatles song, you can say that the words are highly compressible because they're just two words which is repeated many times. So it'll get compressed. You can try it out. You take the lyrics from the internet of that, and you'll just get number nine written over there, and just save it as a text file. You find that it'll compress. Zip. It'll really compress really small. But the cacophony background, the various noises and everything, they won't compress so much because there's no real repeating patterns over there. So that's a contrast between highly complex and extremely simple, juxtaposed over each other. For whatever philosophical reason John Lennon wanted to do that. What has this got to do with architecture? And that is a pretty interesting way by which we can start analyzing and put a number to how complex is a particular project. So for that, I have a very interesting example. Long time back in my final year, I was doing some studies of very, very low cost housing. So I came across this building which was designed for hutman dwellers, jhopatpattis as they are called in Mumbai. So these hutman dwellers, some NGO came and said, okay, we'll give you a proper apartment building. So they removed all the hutmans, and in the same plot they erected these, I think, four-storied buildings, apartments. And the design, I actually can explain it to it quite verbally. I was quite kind of found it too simplistic actually, because it's very raw and crude, frankly. So let me describe that. So you have a staircase, and then you have a landing, and there are two flats opposite each other. From the landing, you open the main door, you get into a rectangular room. That's a living room. And right up on the opposite wall of the living room, so you're hitting bang in the center of the that rectangle, the longer side of the rectangle. Bang opposite is another doorway, which leads to a small little, you can call it a corridor or a foyer. And on the left of that is a WC. On the right of that is a bath. And on the opposite wall of that lobby is an opening which goes into another rectangular room, which is the kitchen. That's it. That's that's what the design was. So if you were to open the main door of that apartment, you'll see right through, right till the end of the kitchen. It was just a room kitchen with bath and WC. Poor people, so for some reason, people think poor people are very small and tiny and they have very tiny requirements. But that's a philosophical argument. For whatever reason, that NGO decided to give just this. So I was damn curious because it was quite a crude design, according to me, because there was no real privacy. You just walk in and you bang into the living room and you can bang into the toilets, sorry, the WC and bath, and you go into the kitchen. There's nothing else over there. They're all small rectangles, that's it. So I went and met the architect actually. And he had a very good explanation about this. He said that in any design, there will be hidden corridors, right? People have to walk from one opening to another opening, right? So I said, yeah, that is true. So I said, how much more efficient can one get other than a straight line? Which is true, right? If you were to go at an angle, if a doorway was here and the other doorway was here, so that would be going at an angle, which means it'll take a longer distance and it'll occupy more space. So he just put all the doorways one opposite the other, and thereby you got just one hidden corridor going through various doorways, and then you go into the kitchen. That's it. So practically, people are just stuck in that circulation up and down from the kitchen back to the main door and all that. In one of my earlier talks, I had talked about palindromes, where I said that let us put a symbolic name to each of these spaces, including the doorways. So let's say the kitchen is A, the doorway is B, the lobby is C, the doorway from the lobby to the uh, living room. Where were we? A, B, C, D. Okay, so D and E, and the main door is F. So if somebody was in the kitchen and the main door was rung by somebody else, so you come traveling down from A, B, C, D, E, F, reach the door and retrace back F, E, D, C, B, A. That's it. There's nothing else happening in that. I mean, there is the sideways entry into the toilet, WC, and the bath. But other than that, that's it. That's the only thing which is going on there. Now, if you were to look at this from this K complexity method, which I just told you, and if you say, okay, let us now look at this particular design with the number of palindromes which are existing, palindrome being the number of uh, pathways. In fact, it's not just palindromes. You could have a circular path also. In some complex projects, you will start from one direction, move on to the whole thing, and then retrace from another point and reach the main door. You could do that way also. So you have various such patterns or sequences of circulation, and then you can symbolically assign it with this alphabet. So you say A B C D E F G H I J K A, whatever. If it's a circular one, if it's a palindrome, it'll go A B C D E and E D C B A. That kind of thing. So what you can do, what one can do as an architect, is to figure out how many such patterns are there, put them all together, and then try to compress all of them together. In fact, you should compress each of them and then find out the ratio and then do some mathematics based on the frequency of the usage of that circulation. That's for later. That's let me not complicate this discussion. So now what happens is you have a pretty interesting and a pretty accurate method which measures how simple or complex are the circulations going on inside these spaces. Then what we have to do is to, we do not know, we'll just get some numbers, that's it. So just by one person doing this, it won't be sufficient. That's why I said it's just a interesting theory which needs to be followed up further. So what we need to do is to have a corpus of data where architects doing such projects will announce the K complexity of their individual circulation in various types of building typologies, houses, apartments, housing for the poor and whatnot, and slum dwellings and pavement dwellings, whatever the case may be. And this can be done right across the spectrum because we are now talking only about spaces. I have not referred to any walls or anything like that. So now what happens is once we have a particular corpus of a lot of this data of this K complexity values, now you have a target to meet, right? So you have been given a particular project And then you, one of your higher motives is motivations would be to make it very lovable and nice, like that grandparents' house. And so you look up the K value for such type of dwellings, and then you work out various alternatives, and then you measure it and measure the K complexity, and then you figure out which measurement will really fit that particular value which has been mentioned in that corpus of data. Which, so this is a lot of work and it requires a lot of cooperation. So that's why it's still a hypothesis, and it's a pretty interesting way to really look at architecture, and it gives you some material to ponder over. Now, some people kind of think that this may, all this maths and all, God, the feeling of architecture is going away and all that. Well, I have some surprising news for you. Uh, Music, art, everything has got a lot of intricacy and a lot of such art, music. Like I just gave you an explanation of Beatles' Strange song. Probably the strangest song the Beatles composed is that one. Maths is everywhere, and that doesn't detract you from the finer philosophies of your design. So I'm not touching there, not going there, because you are anyway going to think about it. So you don't need me to give some explanation about your subjective values. It's still with you. So that's always going to be at work when you're making those different alternatives. You would be considering many things. It's not just these K values. So there you have it. This is a pretty interesting way by which my software TAD can be used to work out these K values and then come up with data which can be used cooperatively by other architects. And then we have now some teeth into this argument on how do we make our designs, and how do we predict that there's a good chance that this will lead to some pretty useful circulation patterns which people may start enjoying and start thriving in. So take a look at my software. It is called TAD, and it is pretty interesting to work on that. And all this work can be done over there. Thank you very much. I hope to see you in my next video. Thank you.